Well, let's jump right in. Welcome to the Explainer. Today, we're taking on what honestly feels like a massive challenge. Our goal is to translate the dense and sometimes totally overwhelming text of the 2023 National Electrical Code into actionable, high-yield job site realities. We're zeroing in specifically on Articles 210 and 220, the sections covering branch circuits and load calculations. So whether you're prepping for a huge exam or you just want to completely bulletproof your code knowledge on the job site, you are exactly in the right place. We're going to break down the math, the rules, and the actual reasoning behind all of it, step by step. Here is our roadmap for the session. We'll start with number 1, essential definitions. Then 2, protection and placement rules. 3, conductor penalties. 4, appliance demand factors. And finally, number 5, standard dwelling calculations. Section 1, essential definitions. Okay, let's dive right into this. To master these calculations, you really have to speak the language perfectly. These heavily tested glossary terms are going to form our absolute baseline. On a real-world job site, the single definition changes everything about how you wire a circuit. If a load is running at its maximum current or more, it generates sustained, trapped heat. To combat this, the NEC hands you an automatic 125% impacity penalty. You literally cannot just size the wire for the load itself, you have to size it for 125% of that load just to safely handle that continuous thermal stress. Now, think of ampacity as our ultimate target number. It is basically the lifeblood of our conductor sizing. When we start pitting environmental heat penalties against those continuous load penalties we just talked about, ampacity is the exact rating we are desperately trying not to exceed. Section 2, protection and placement rules. All right, moving into some practical everyday applications. A massive part of knowing the code is knowing exactly where to put your life safety devices. Let's look at the critical differences between AFCI and GFCI requirements. The absolute easiest way to keep these straight, especially if you're taking an exam, is using a living space versus wet space reality check. AFCI, which stands for arc fault circuit interrupters, are required in habitable, normally occupied spaces. Think bedrooms, living rooms, and hallways. They are designed to prevent fires from arcing wires. GFCI, on the other hand, ground fault circuit interrupters, are all about preventing fatal shock in wet, damp, or unfinished areas. That means your bathrooms, kitchens, garages, crawl spaces, and anything outdoors. Now, I want to highlight an absolutely crucial, high-yield number for the 2023 code cycle. For kitchen islands and peninsulas, receptacle outlets can no longer just be cut right into the sides of the base cabinets. Instead, if they're installed, they have to be mounted on or not more than 20 inches above the countertop surface. This is a massive shift in how we approach island wiring, so definitely commit that one to memory. Section 3, conductor sizing and penalties. All right, time to build some excitement because we are entering the penalty A versus penalty B arena. When multiple conditions try to derate your conductor at the same time, how do you know which wire size to actually pull? Let's take a sports commentator approach to this. Picture this. Classic, high-stakes exam scenario. You got a 95 amp load. It's running continuous. And just to make it absolutely brutal, it's sitting in 120-degree Fahrenheit ambient temperature. You literally have 2 different penalties attacking your wire's ampacity at once. Take a second. How do you solve this? Okay, here is the golden rule. You do not apply both of these penalties at the same time. You work them out completely separately and let them fight it out. In step 1, we calculate the continuous load penalty. 95 amps times 1.25 equals 119 amps. In step 2, we calculate the ambient temperature penalty. Using our code tables for THHN at 120 degrees, our correction factor is 0.82. So 95 divided by 0.82 equals 116 amps. Step 3, you just choose the larger resulting number. The 119 amps wins out, meaning we must pull a number 1 AWG copper wire. Let's challenge ourselves again. What happens when conduit fill enters the ring? We have a 145 amp continuous load, but this time we have 8 current carrying conductors crammed inside the exact same pipe. Conduit fill is a notorious job site issue because it severely traps heat and plummets your wire ampacity. Watch what happens here. It's wild. In step 1, our continuous load multiplier gives us 181 amps. But in step 2, our conduit fill penalty for 8 conductors means we have to divide by a 0.70 adjustment factor. 145 divided by 0.70 skyrockets our requirement to 207 amps. The conduit fill penalty completely overpowered the continuous load penalty in this scenario. So we have to size for 207 amps, which requires a massive 4Ah AWG THWN copper conductor.
Section 4, Appliance Demand Factors. So how exactly does the NEC handle multiple large appliances sharing a feeder? Because let's be real, the code recognizes that not everything in a house runs at maximum capacity at the exact same second.
Think of this as a quick recipe that you just need to memorize for your exam. Section 220.53 allows a 75% discount, what they call a demand factor, if you have 4 or more fastened in-place appliances on the same feeder. But they must be rated a quarter horsepower or 500 watts or greater. This includes things like dishwashers, garbage disposals, water heaters, and trash compactors. Be careful, though. It strictly excludes household cooking equipment, clothes dryers, and HVAC systems. Speaking of cooking equipment, let's look at Table 220.55 for household electric ranges. I know it looks notoriously intimidating, but let's simplify it right now. Columns A and B, those are just percentages. You apply those percentages directly to the nameplate rating of the appliances, but column C is completely different. It is a hard kilowatt rating. For example, the maximum demand for a standard 12 kilowatt range in column C is simply a flat 8 kilowatts. Easy. But what if you have one of those massive luxury ranges? Remember this critical high-yield calculation trick. If an electric range exceeds 12 kilowatts, you take that 8 kilowatt baseline from column C and you increase it by 5% for every single kilowatt the range goes over 12. So a 16 kilowatt range is 4 kilowatts over the limit. 4 times 5% is a 20% increase.
Section 5, Standard Dwelling Calculations. Okay, take a deep breath. We are officially gearing up for the final boss fight of this explainer. We're going to put all the pieces together for a standard whole house dwelling calculation. It all starts with this number right here, 3 volt amps. 3 volt amps per square foot is the absolute baseline minimum unit load for general lighting and general purpose receptacles in a home. When you multiply the home square footage by 3, you are calculating the base general lighting load. But hold on, you're not done. You absolutely must remember to add these mandatory circuits to every single standard dwelling calculation before doing anything else. The code requires at least 2 20-amp small appliance branch circuits for the kitchen, and those are calculated at 1500 volt amps each. Plus, you need 1 laundry branch circuit at 1500 volt amps. That is a mandatory 4500 volt amps stacked right on top of your square footage load. So let's frame this as the ultimate test question. Try to combine the 3VA rule and those mandatory circuits we just discussed to find the total minimum lighting load for a 2500 square foot home. Any guesses? Let's break down the math clearly. Step 1, 2500 square feet times 3VA gives us 7500 volt amps. Step 2, we add our 3000 VA for the kitchen circuits and our 1500 VA for the laundry. Step 3, that gives us a grand total of 12,000 volt amps, and that's before we apply any demand factors. And this brilliantly illustrates how the NEC saves you from putting massive, completely unnecessary electrical services on standard homes. Using Table 220.45, the code essentially assumes you aren't going to have every single light, TV, and kitchen gadget turned on at once. We take the first 3,000 VA at 100%, but the remaining 9,000 VA, that gets discounted all the way down to 35%, which is 3,150. Add them up, and our final lighting load drops drastically down to just 6150 volt amps. Finally, as you calculate the loads for all these phases, do not forget the neutral. Section 220.61a dictates that the feeder neutral load is the maximum unbalance between the neutral and the largest load connected to any one phase. Essentially, neutral conductors don't care about perfectly balanced loads. They only care about worst-case scenarios, like when loads on the other phase are completely shut off. We've covered continuous loads, ambient temperatures, conduit fill, appliance demand factors, and the ultimate boss fight of whole house calculations. Remember, the code isn't just arbitrary math. It's a finely tuned, highly practical system for managing thermal stress and human behavior. But as our homes get smarter and we add massive new loads, like EV chargers, into the mix, how will these calculations shift in the next code cycle? It's something to think about. Until then, hit the books, run the numbers, and stay safe out there.